So today we're going to review another section of Eric Dollard's paper on the symbolic representation of the generalized electric wave. Okay, so what I'm going to do is I'm going to read this section of the paper and then we're going to have a discussion of it. But I want to do this from the perspective of the principle of incommensurability and the notation that I've been developing to represent incommensurate principles. So this is the section we're going to be reviewing. It's called, it's section 2.4, types of current. And so Eric Dollard identifies 4 types of current. This is a picture of 3 of the 4 types of current. This is impulse, this would be an impulse current. This is alternating current right here. And down here is what he is referring to as oscillating current. And of course, direct current would just be a flat line, a single line. And he also shows these 2 figures in his paper, figure 1 and figure 2. And these are the signals that are generated when you are switching. Okay, so it's caused by this picture up here is caused by switching of a 154 mile, 100,000 volt transmission line. Okay, and this one down here is an oscillogram of oscillating compound circuit consisting of 154 miles of 100,000 volts of a step-up transformer connecting and disconnecting, in other words, switching. Okay, so switching is the key word here. So what I'm going to do next is I'm going to read this section of the paper, which is not very big, and then I'm going to show you how I apply what Eric Dollard is saying to the principle of incommensurability. In the study of electric phenomenon, attention is usually focused on only 2 forms of electric waves, those of alternating current, AC, and continuous or direct current, DC. While these forms are representative of commercial application of electric energy, they only represent special steady-state cases. It is known that during switching operations and in the process of modulation, other forms of electric waves appear due to energy readjustment within the electric system. These waves are known as electric transients. Okay, we've talked about transients before. Transients are temporary conditions. Okay, so theoretical understanding of these phenomenon is usually quite vague. So transients aren't as studied, I guess, as the standard commercial, the energy for commercial applications, or the waves, the electric waves for commercial application, AC and DC. So, these transients give rise to a new pair of waveforms, the oscillating currents and the impulse currents, OC and IC. Thus, in general, the variation of electric quantities with respect to time may be divided into 4 distinct categories. Continuous currents, which he refers to as DC, alternating currents, AC, and impulse currents, IC, and oscillating currents, OC. Okay, and then he gives the time function of each of these these currents. So basically how they're changing with respect to time. And so of course, direct current, continuous current, direct current does not change with respect to time. So its time function is 0. Alternating currents do change with respect to time. They alternate equally over time. And so the units for this for alternating currents are radians per second. Impulse currents also change over time, and the units for the time function of the impulse currents are nepers per second. Now, what the heck is a neper? Okay, I actually hadn't heard of this term before I read this paper. So the neper is a logarithmic unit for ratios of power. Okay, so the neper is related to quantities that change in magnitude over time. So the neper is a hidden unit that probably most people don't write, and it is analogous to radians, which is also a kind of a hidden unit that most people don't write. And so these are in fact units. As you know, before I identified the units of 2 pi, right, to be radians per cycle. Okay, 2 pi are the number of radians in one complete cycle. Okay, so nepers is the unit of change in power, change in amplitude, change in the magnitude of the wave. And then there is oscillating currents. So oscillating currents have a time function of nepers radians per second, and this is because it is both alternating and it is changing in amplitude over time. So it is kind of a hybrid of the alternating current and the impulse current. The continuous currents represent the continuous time invariant or scalar component of the generalized electric wave. The alternating current represents the continuous but cyclic variation component of the wave. The impulse currents represent the discontinuous or acyclic component of the wave. The oscillating currents represent alternating currents that grow or decay with respect to time, thus being a combination or a hybrid of cyclic and acyclic variation, AC and impulse. So the oscillating currents appear to be a hybrid of impulse and AC, in my opinion. So that is just a quick overview of all of the types of currents that Eric Dollard identifies in his paper. So as a review, we've got, he identifies 4 types of current. He's got the continuous DC. Okay, he's got the alternating current with the time function radians per second. So this is in terms of radians. And he's got the impulse currents, which have the time function has units nepers per second. And nepers, again, is a logarithmic unit for ratios of power. Okay, so this is new. I hadn't heard of this before. Radians and nepers are kind of hidden units in the unit sections of equations, and generally they're not written. And then we've got the oscillating currents, which seem to be a hybrid of impulse and alternating currents because they have units, nepers, radians per second. So it's got both of these units in oscillating currents have nepers and radians per second. So it is a hybrid or a combination of the alternating current and the impulse current. So next, what I'm going to do, or at least try to do, is to put these different types of currents into my complex notation, which is related to the principle of incommensurability. And so this is just a sketch of the complex notation. As you know, in the complex notation, the scalar is on the forward diagonal, and the thing that is cyclic, the thing that has positive and negative, or maybe it's clockwise, counterclockwise, the thing that can have opposite sense goes on the backward diagonal. And so I just want to point out that this is just a notation that I'm using. I'm not saying that you can use this mathematically necessarily, although I'm not ruling it out. Okay, so this is just notation to try to deduce what the incommensurate principles are in these different types of currents. And so if I were going to place these different types of currents into my complex notation, this is what I would do. Okay, so obviously DC, the DC current, would go on the forward diagonal because the continuous DC currents represent the continuous time invariant or scalar component of the generalized electric wave. So DC, obviously, if I were going to put it into my complex notation, since the scalar is on the forward diagonal, I would put DC on the forward diagonal. And in a similar manner, since AC, alternating current, has it alternates from positive to negative, or forward to backward, or clockwise to counterclockwise, however you are visualizing alternating currents. The alternating current I would put on the backward diagonal of the complex notation. So the alternating currents represent the continuous cyclic variation component of the wave. So in my notation, anything that has a cyclic, that is cyclic over time, I would put on the backward diagonal of my complex notation. So that could be clockwise, counterclockwise. That could be, positive and negative charge. So if it's cyclic and or has a positive and negative sense, has a positive and negative sense, then which are opposite, equal and opposite, then I would put that onto the backward diagonal of my complex notation. So what about impulse currents and oscillating currents? How do they fit into this complex notation? Well, the impulse currents are not oscillating in any way, shape, or form. Technically, they are, let's just have a look at the picture here of an impulse current. An impulse current has magnitude only that magnitude changes over time, but it is not cyclic. It does not oscillate, and so it is technically a scalar. Scalars can change over time, obviously. This just has magnitude. Anything that only has magnitude and not a positive and negative, equal and opposite, positive and negative sense, like charge or alternating current, I would put on the forward diagonal of my complex notation. In a similar manner, since oscillating circuits are oscillating. I would put oscillating currents on the backward diagonal of my complex notation. But is this the right thing to do? Is this the right thing to do? This doesn't seem right to me because oscillating currents appear to be a hybrid of alternating currents and impulse currents. And so you can create an oscillating current with an alternating current superimposed with an impulse current. Okay, as you can see here. So an alternating current is a current that oscillates, but it also either expands or decays with time. Okay, so I'm not convinced. Okay, I'm not convinced that this is the right thing to do. Using just a little bit of intuition, I decided to write this down. So we know that the impulse current belongs on the forward diagonal and the alternating current belongs on the backward diagonal. And so this is what I would actually write in my complex notation. Impulse current and alternating current together work together to create oscillating currents. And so where does that leave direct current? So if this is the proper representation, complex representation of currents in my complex notation, where does DC fit in? So it seems like I should be putting DC on the forward diagonal. Okay, so I could do that. But then using DC and AC, I can't get oscillating currents. Okay, and using DC and AC, I also can't produce impulse currents. And so in order for this to be correct, impulse currents there needs to be a way to use impulse currents to create direct current. Okay, direct current needs to be a special case of impulse currents in order for this to be correct. So my proposal here is that DC is a special case of impulse current. So let's see what Eric Dollard has to say about this. So in section 2.5 of his paper, Continuous Current, he says the following: the continuous current can be resolved into a pair of superimposed impulse currents, one impulse growing in amplitude with respect to time, representing the production of electrical energy, the other impulse decaying in amplitude with respect to time, representing the consumption of energy. If the two rates are equal and opposite, and the two amplitudes are unequal, that's the important part, the resultant wave is a direct or continuous current. So basically what Eric Dollard is saying here is that DC is a special case of impulse currents. And so it makes sense then that this complex notation that I developed here puts impulse current on the forward diagonal, alternating current on the backward diagonal, and OC, oscillating current, is a hybrid of impulse current and alternating current, and DC, okay, is a special case of impulse current. Okay, so DC, I could put DC on the forward diagonal, but it is only a special case of impulse current according to Eric Dollard, and so it makes more sense to put impulse current on the forward diagonal, alternating current on the backward diagonal, and with this complex notation, we can produce direct current and oscillating current. So this is a representation in my opinion, because I don't think Eric Dollard would necessarily agree with this, but this is the notation that I would select for my principle of incommensurability. So then I would go on to say that impulse current and alternating current are incommensurate principles. Impulse current and alternating current are not alike. They are not anything like each other. One is a scalar, which changes over time, and one is alternates and doesn't change over time. Okay, so so this is what I would write if I were going to put you know, these different types of currents into my principle of incommensurability. So the reason I think that Eric Dollard might not agree with me on this is because in section 2.5, where he talks about direct current being able to be produced with two impulse currents, he goes on to say, likewise, an alternating current can be resolved into a pair of superimposed oscillating currents, one oscillation growing in amplitude with respect to time, representing the production of electric energy, and the other oscillation decaying in amplitude with respect to time, representing the consumption of electric energy. If the two rates are equal and opposite, and the two amplitudes are unequal, the resulting wave is an alternating current. So he is kind of creating an analogy between what he said about the impulse currents and what he says about the alternating currents, but I don't actually, this part here bothers me a little bit because it doesn't fit in with, so basically he's saying that impulse current and oscillating current, you know, should go like this in my complex notation. But the reason I don't agree with this is because there's no, the impulse current, the oscillating current has impulse current built into it, and so these cannot be incommensurate principles. There is a similarity between impulse current and oscillating current in that the impulse is built into the oscillating current, and so I don't think this is correct right here. And so I'm using the principle of incommensurability to tell me what is correct and what is not correct. So this actually makes more sense to me. It makes more sense to me that impulse current and alternating current are incommensurate principles. Impulse current grows and decays over time, and alternating current doesn't. Alternating current oscillates and impulse current doesn't. So they're, you know, part of the principle of incommensurability is that the two incommensurate principles have to be orthogonal. They have to be very different from each other. And so I believe that this is the right thing to do. The other reason that this makes sense is because the alternating currents have units radians per second. The impulse currents have units nepers per second, and so nepers being a scalar, i.e. it is the, let's go back to the neper again, neper is a logarithmic unit, it's a unit of scale. Okay, so the neper belongs on the forward diagonal because it is a scalar unit, and radians belongs on the backward diagonal because it is a cyclic unit. And so this, using the principle of incommensurability, I was able to deduce that, you know, that impulse current and alternating current are incommensurate principles. Impulse currents, according to Eric Dollard, can be used to generate direct current, and alternating currents and impulse currents together can generate the oscillating currents, this other wave that is, you know, a little more complicated. Okay, so so that's the point I want to make. I want to show you how I'm using the principle of incommensurability to further decode what Eric Dollard is saying in his paper. And so Again, I want to emphasize that this is just a notation that I'm using. I'm not saying that you could plug values in here to get sensible results, although I'm not ruling it out as well. Okay, this is just notation to help me sort out in my mind what principles are incommensurate and what principles aren't. So the scalar goes on the forward diagonal, the cyclic, polarized, anything that has a plus or minus or a clockwise counterclockwise or anything that can be associated with cyclic phenomenon goes on the backward diagonal. Okay, so that is the principle of incommensurability as applied to the concept of current. Okay, so that's all I'm going to do for now, and I hope everyone is having a good day.